All right, so we're going to continue our discussion of Newton's laws. And we're going to do so by bringing up the concept of contact forces, which we did talk about a little bit last week. I'm just going to sort of, again, point out that there are these contact forces things. And I'm going to specifically mention normal and friction. Now, in your textbook, you will see that the book goes through and talks about sort of each force individually, and then at the end in chapter 6, it's sort of like applications. I kind of do it that way, but I kind of don't think it's necessary to split the two up. As we're talking about each of these forces, we're going to apply them in the form of examples. Okay, so we're sort of combining chapters 5 and 6, and then I'm going to rearrange chapter 6. It's going to be all sorts of fun. But we're going to cover all the material one way or another. So I don't want you to get too angry at me. We did talk about the normal force yesterday. It's the force that acts between the interface of two surfaces. So if you have a table and you throw a book on it, a book is, of course, a rectangle. The book has a normal force that is due to the table. That normal force is pointing in a direction. Let's make the direction green. Maybe not. Perpendicular to the surface. Which is that thing. All right, so that's the normal force. I'm not going to say anything more about it because we've dealt with it, so we're just going to jump into an example. We're going to start to, I need an adjective, or I need a verb here. We're going to start to complicatify. Complicatify our examples. That work? All right, so this is the example of the sled. How about not there? All right, so a sled is tied to a tree. I should note that I really try to avoid, I'm not sure if I did this on the first day of class, I try to avoid using examples in your book because you guys have the book. You don't need me to read your book and do the examples for you when they're already in the book. So I generally try to do examples that aren't in your book. Sometimes they'll be pretty similar. But basically the goal here is to give you, extra examples. So if you ever do an example in your book and you don't understand it, definitely ask me, in office hours, email, or something like that. But I'm trying to give you more stuff to study with. So this example is: a sled is tied to a tree on a frictionless snowy hill. If I want to know if the sled weighs 77 newtons, I want you to tell me the magnitude of the force applied by the string that's holding the sled in place, and the normal force. All right, so a sled tied to a tree, figure out what is the force applied by the string and what is the normal force. So if I draw you a picture, it's going to look something like this. There's the hill. The tree is up here. I only draw bottoms of trees. And there's a rope. The rope is horizontal to the hill, perpendicular to the hill, I should say. And it's attached to the sled. All right. I need to give you an angle, so I'm going to do that. This is 30 degrees. So we're starting to go on angles now. You're going to see lots of these things. We usually call these planes. Inclined planes is a very physicsy term that we'll use. All right, so you got a sled on a plane attached to a string. So we have a picture. I'm going to define a coordinate system. And it's going to look like this. Y and X, just like normal. So the first thing I want to do now that I have my picture and my coordinate system is label the forces. All right, so I could draw another diagram. I'm just going to use this as my free body diagram since it's relatively uncluttered. So somebody tell me about the forces. Gravity. Normal force. What else?
Tension. tension on the rope.
All right, the tension in the string. I'll call that tension T. That is a force that we'll sort of mention. That is this tension is a force. I didn't call it tension up here just because I didn't want to get into it. But tension is a force that we do encounter. What else?
Do we care about the tree?
We don't care about anything acting on the tree. We're talking about the sled. So the sled is the object we're interested in. All we want to know about are the forces acting on the sled. Anything else? No friction. It's frictionless.
Wouldn't the hill have a force?
I'm sorry?
The hill would have a force on the sled.
Well, the force of the hill on the sled is the normal force. Exactly. Yep. So that's what the normal force is. It's coming from the hill. The weight of the sled is the force due to gravity. That's it. All right. There is no imaginary force pointing down the hill or anything like that. So yeah, this is it. I just didn't want to say it, but that's it. All right. So we've got our free body diagram. All right. Now I'm gonna put my coordinate system on top just so that we can see it. I wonder if I use gray. How would that look? Ooh, that's kind of straight. Yeah, I like that. All right, so that's my coordinate system. So we can see that we have one force that lies right on the y-axis. We have two forces that do not, which means that we are going to have to break these things up into their components. Just draw that like so. All right, so let me do this side. All right, so the normal force has a component in both the x and the y direction. This is the normal force Fn sub x. This side is Fn sub y. This tension also has two components. This side is I'm calling it T. This is T sub x. This side is T sub y. All right. Once I break up all my vectors into the components, then I could add them like normal numbers, just like you're doing in kinematics. So that's the first step. Well, not the first step, but that's one of the steps that I listed yesterday when we were talking about what we're doing here. All right, so let's go ahead and do just that. Now we're going to solve Newton's second law. Newton's second law is what? F equals ma. So we're going to solve that. We need to solve it in two directions, right? We want to know what the tension is. We want to know what the normal force is. So we're going to solve that guy in two dimensions. Which direction do you want to do first? All right, it doesn't matter. We do x direction first. So the sum of the forces in the x direction, I'm just going to add up all the forces. The tension points to the right, so that's where we said that's positive. So T sub x. There's a normal force pointing to the left, so that's got to be subtracted, Fn sub x. That's it. There's just two forces in the x direction, the x component of the tension and the x component of the normal force. The sled is tied to the tree. It's not going anywhere, so there is no acceleration. So this is equal to mass times acceleration in the x direction, which is 0. So I'm left with here is T sub x minus Fn sub x is equal to 0. So in the x direction, the tension, the x component of the tension is balancing the x component of the normal force. They're in balance. Now, I could do something with this because I don't really care about T sub x. What I care about is T. I don't care about Fnx. I care about Fn. Right? So I can do some trig here, and I can write these guys out in terms of tension and the normal force. In order to do that, though, I need to know some angles. I've got two right triangles here. I need to know some angles. Who can tell me about the angles? So let's look at this one. The red line to Tx. What's this angle right here? That is 30 degrees. What is this angle right here? That's the hard one. This one. It's probably even, it's either 30 or 120. It's got to be bigger than 90 to be 120. So it's either 30 or 60, because this one's 30 and the complement of 30 is 60. The way I've drawn it, it kind of looks like it's 30, but can you convince yourself that that's 30?
30, and then shouldn't that be 90 degrees above?
No, I think it's 30. I think it's
All right, let me tell you, there's two different ways to do this. This is 30 degrees.
Yeah, because it's 90 degrees solve where tension
There's
is?
3 different ways. You wait for the professor to tell you, or you do it yourself. All right, so here's the 2 different ways to do this. These 2 red lines, the vectors, okay, they're perpendicular, right? Because this is the normal force. Tension is along the ground, so they're perpendicular, right? In order to get to this vector, so in other words, the angle from, let me see here, the angle from my y-axis to my x-axis, that's 90 degrees. The angle from here to here is 90 degrees. So what I really want to know is what's the angle from here all the way back down to my x-axis. Well, if this is 90 and this is 30, that must be 120. But I'm not going from there, I'm going from this axis. So 120 minus 90, because that's this chunk, is just 30. Okay, now that I was making a lot of motions with my mouse. The way that I always do this is I just look at, okay, what I did is I sort of rotated from, I rotated counterclockwise from my x-axis to get to tension 30 degrees. So if I rotate counterclockwise from my y-axis to my new vector, then I should be at the same angle. So counterclockwise from the y-axis to this new vector is 30 degrees, because those 2 are parallel. So one way or another, figure out that you can convince yourself that that's 30 degrees. If you really want to do it how a mathematician would tell you, you'd figure out that the angle from the x-axis to here is 120. And then you have to subtract off 90 to get 30. All right, but we're going to do this a few times, so make sure one way or another you're happy with how you can figure that out. So now we can break things into the components. T sub x, that's this side here. It's the side adjacent to my angle, so that means I'm going to be using the cosine. So I've got t times the cosine of 30. That's equal to the normal force. The x component is the side that is opposite. All right, so I said this before. Don't always associate cosine with the x side. All right, it's however you draw your triangle. So here I've got the opposite side, so it's got to be the normal force times the sine of 30. Now I have a problem here because I don't know the normal force and I don't know the tension. So what I'm going to end up having to do here is solve 2 equations simultaneously. When I write down my equation in the y direction, you'll see that I'm going to need to solve them simultaneously. So in order to do that, what I'm going to do is solve for tension. It's equal to the normal force times the sine of 30 divided by cosine of 30, which is just tangent of 30. All right, so that's the tension. In order to really get the tension, I need to know the normal force. So to get the normal force, I can solve in the y direction. So I sum the forces in the y direction. I'm going to have a very similar type of equation. But now I have 3 forces. I have tension, I have the normal force, and I have gravity. All 3. So the y component of tension is this side. It's the side opposite the angle that I know. So it's going to be t times the sine of 30 plus the y component of the normal force, which is also pointing up, which is Fn. This time it's this side. So it's going to be I'm using the side adjacent to the angle, so I'm using cosine. All right, but I have one more force. Now I have the force due to gravity, so I'm going to subtract off mass of the sled times gravity. All right, I actually gave you in the problem statement, I told you that the weight is 77 newtons, so I could just replace this mg as 77 newtons, which I'll do in just a second. All right, once again, I have tension and the normal force. I don't know both of those, so I need to substitute in tension into my second equation here. So I'm going to be left with something long and ugly. The normal force times tangent of 30 degrees times the sine of 30 degrees. All right, I've just put in this value into tension here, plus the normal force times the cosine of 30 degrees, minus mg, which is the weight of the sled. I told you that's 77 newtons, is equal to the mass times the acceleration in the y direction. Again, it's not accelerating at all, so this is just 0. All right, I have one equation now and I have one unknown, so at least I can solve this guy. I can solve that for the normal force. There's lots of tangents and sines and things like that, but it's still solvable. Can everybody solve this equation? Can you do the algebra? I'll run through it, but eventually I'm going to stop solving these types of things. All right, so I'm going to factor out an f sub n.
Don't you have to bring the -77?
Yep, I will move that to the other side. So I'm factoring out the f sub n first with this really ugly thing inside. And then I'm going to move the 77 to the other side, so that's equal to 77 newtons. So what I get is the normal force then is equal to 77 newtons divided by a whole bunch of trig functions. Tangent of 30 degrees times the sine of 30 degrees plus the cosine of 30 degrees. Whew, ugly. Ugly. If you solve that, you get a normal force of 66.7 newtons. And then once I have this normal force, I go back and I plug it in up here. I'll get there eventually. To solve for the tension. So tension is just this number times the tangent of 30. If you solve that, you get the tension is 38.5 newtons. All right, so we got it. Got it with quite a bit of work. All right, so like I said, we're going to look at this problem from a different light. We're gonna tackle this again, but we're going to do something different. One thing differently. All right, that thing that we're going to do differently is instead of using our normal coordinate system like we did in the first problem, we're going to go ahead and rotate our coordinate system. All right, so up here we use this the standard XY horizontal vertical coordinate. I'm gonna postulate that it makes much more sense to say this is our y direction. Remember, we can do this because we can pick our coordinate however we want. And this is our x. So the x direction is parallel to the slope. The y direction is perpendicular. And the reason this makes it easy, or one of the reasons why this makes it easier, you can see right away, instead of having to break up two different vectors into components, we only have to do one now. Because tension just lies in the x direction, the normal force just lies in the y direction. Gravity is the only thing that's moving, that's in between. All right, so that part of it will save us some trouble. In addition to that is what you'll see is that since these the two things we're after, lie along the x and y axes, we don't have to do that simultaneously solving two equations thing. We can write down an equation for the x, we'll solve that for tension. Done, got tension. Write down an equation for y, we solve that for the normal force. Done, we have the normal force. All right. So let's do it. Let's start off solving for, let's solve the x equation first. So we're going to do summation of the forces in the x direction to start. And the first thing I'm going to have to do is resolve the force due to gravity into its x and y components. Sometimes it's tricky to draw this triangle. Remember that you have to draw the triangle sides along the axes. So I'm going to come down here along the y-axis, and I'm going to go left in the negative x direction. So you got to make sure when you're drawing the triangle that both sides are parallel to your axes. So this side is on the axis, so it's parallel, and this side is on this axis. That defines this as the 90 degree. All I'm left with now is choosing which one's going to be 30 degrees in this triangle. I know one of them has to be 30. Got to pick which one. The way that I do this always is start from the original axis was horizontal, which is this side of my slope. My new axis, I rotated counterclockwise 30 degrees. All right. My original axis was the y-axis, which was straight down along force due to gravity. I rotated 30 degrees counterclockwise, which tells me that this side, to get to the new axis, which tells me that this side is 30 degrees. All right. I have an angle. I know that I'm looking for these two sides. The force due to gravity in the y direction is this guy, and then this side right here is force due to gravity and the x direction. So now I can sum up my forces. So in the x direction, I have tension pointing to the right. That's just tension. Pointing to the left, I've got the x component of gravity. Those have got to be equal to mass times acceleration in the x direction, which is 0. I solve that for tension. It's equal to I move the force due to gravity onto the right side, which is just mass times gravity, and I gave you that as 70, was it 77? 77. Oh, it's not, that's the weight of the sled, right? Okay, 77 newtons, okay, yep, that's right. For some reason, I'm looking at this equation all confused. So it's 77 newtons, and then the x component is not the cosine. Again, we have this angle, and we're looking for this side, so it's got to be the sine of 30 degrees. If you solve that, you get 38.5 newtons, which is what I get up here. All right, so I got the tension. I didn't have to simultaneously solve two equations to do it. In the y direction, I write down another equation that's very similar. The sum of the forces in the y direction, I have the normal force pointing straight up, or at least straight up according to my y-axis. I subtract off the y component of gravity. That's equal to mass times acceleration in the y direction, which is 0. Again, the sled is not accelerating. So I can write down the equation. The normal force is equal to the force of gravity in the y direction. Those two are in balance. So that's going to be 77 times the cosine of 30, which is equal to 66.7 newtons. All right, so I solved it two different ways. I got the same answer. I would say that this way is easier. Hopefully you agree. Pretty much anytime you do an inclined plane problem like this, it will be easier if you rotate the coordinate system. Every now and again, it's not easier, but it's not harder. It's the same. All right? But usually it's easier. All right, let me try to point out one more reason why this will be easier. Let's say that this thing was accelerating. All right, so let's do a similar problem, and we're just going to cut the cord. Okay? Were there any questions up here, by the way? Before I move on. Anything I did up here? Questions? Yeah.
Could you explain quickly again how you knew which angle would be for these positions?
Sure. So what I do is, all right, so what I did, I had my initial x-axis was like this. My initial y-axis was like that. In order to get to the slope that I have, what I did is the slope is rotated this way. I went 30 degrees counterclockwise. So I went up this way to give myself a slope of 30 degrees. Okay? So what I did is I took my original x-axis and I rotated 30 degrees to get my new x-axis. Right? So what that means then is if I take my original y-axis and I rotate 30 degrees counterclockwise, I'm going to get my new y-axis. So here is my original y-axis was, if I draw it like this, was straight up. If I rotate 30 degrees, this is my original. If I rotate 30 degrees, I get my new y-axis. I know this is my new y-axis. I know this is my original axis, so this must be 30 degrees. All right? And I did the same thing just on the bottom here. So this was my original y-axis straight down. My new y-axis is over here. To get from the original to the new one, I rotated 30 degrees counterclockwise. That's how I do it. I think that's easier than trying to do addition and subtraction of angles and things like that. I just think about how did I rotate from the original to the new axis, and then I look at my vectors. Just take some practice, so do it on the homework, do it in the examples, and you'll get used to it. All right, so let me do a similar sort of setup here. We'll do this one quick. Again, 30 degrees. Again, sled on a hill. This time we cut the rope. All right, there's no tree holding on, so this thing's going to accelerate. So this is the normal force pointing straight down is gravity. All right, what direction is this thing going to accelerate? There's no friction. Negative x, so it's going to accelerate down the slope. It's going to accelerate this direction. If I don't rotate my coordinate system and I use my normal coordinate system, all right, so I use this. All right, I only have two vectors. So my force due to gravity vector, that lies in the y direction in my normal everyday coordinate system. So I don't have to break that thing up into its components. All right. The normal force, though, I do have to break that up. So you can make the argument, well, you only have to break up one vector. If I rotate your coordinate system now, if you rotate the coordinate system, like so, in this case we have to do one breakup. All right. We just have to break up the normal force. In this case now, the y direction is going to be parallel to the normal force, so I don't have to break that guy up into its components. But the gravity, now I'm going to have to break that one up. So this is, again, one breakup. Okay, so you're like, well, why would I rotate the coordinate system then? Because I'm not saving anything on breaking up my force vectors. But what you are saving on is this acceleration vector. If I want to know the acceleration, well, in my original coordinate system, my acceleration is not in the x or the y direction. But in this coordinate system, the acceleration is along the x direction. So I do save a little bit of effort here because I don't have to mess around with doing any sort of trig to figure out the acceleration. Okay, so like I said, generally rotating your coordinate system does make it easier. So I'm going to just really quickly cruise through this. This is actually it's a little bit simpler than the problem we just did, even though there's an acceleration, because the equations look a little bit easier. So this is our coordinate system. I'm rotating it like so. This angle is 30. My triangle looks like this. All right, so in the x direction, the net force, the only force acting in the x direction is gravity. So it's FGX, and it's got to be, since there's only one force, there has to be an acceleration. We know it's going to accelerate, so that's the equation. FGX equals MAX. All right? My acceleration is only in the x direction, so I don't even have to look at the y direction in this problem. All right? So if I solve for the force due to gravity, what I get then is 77 newtons is equal to mass times acceleration of the x. And then this starts to, wait a second, I don't have the mass or something like that. But you do have the mass because 77 newtons has the mass in it. So we know that this is actually mass times gravity times, oh, I'm sorry, I skipped a step, didn't I? Don't let me cheat. Don't let me cheat. Silly, that would give me a very silly answer. Sorry, I forgot to break up gravity into its x component. So I got to include that sine of 30. And that's equal to mass times acceleration in the x direction. So this 77 is just mass times gravity times the sine of 30 divided by mass. So mass actually isn't important. The acceleration in this case is just gravity times the sine of 30. So this is the other thing I wanted to get to. Does this make sense that the acceleration doesn't depend on mass? Well, it is frictionless. Actually, as it turns out, even if there was friction, it wouldn't depend on mass. Not necessarily. All right, so this is actually kind of an interesting result. And the way that I know that this is right, or one of the ways that I can check that this is right, is take a look at this sine term, right? So say, all right, so this is for 30 degrees, but let's say we change that angle. Let's say there was no angle. Let's say the angle was 0. What's the acceleration? What would I expect the acceleration to be if there was no angle? 0. Well, the sine of 0 is 0, so I'd get acceleration of 0. So physically, the math agrees with what I know to be true. If this was straight up and down, the slope was straight up and down, what do I expect the acceleration to be? Gravity. So sine of 90 degrees is 1, so acceleration would just be gravity. Right? So even if I look at this answer and say, I think that's right, but I'm not 100% sure, there's ways that we can test it. You know, take a look at the limits, what we call the limits of the problem, to make sure that it makes sense. This is actually a practice that it's a good habit to get into, because when you study problems that you don't have a good physical sense for a very specific case, you can always go try to apply your solutions to a more general case. We do this all the time in physics. All right, so then we just did a bunch of 3 examples, all very similar. So just to get practice of Newton's second law, and we're going to keep doing more of these, and then your homework is going to be doing all sorts of these guys. All right, so now let's talk about something new. Let's talk about friction. everything we've been doing up until this point, we've been ignoring friction. It's time to make the real world look a little bit more like the world that we've been studying in class. So friction is a force that acts to resist motion. Okay, or oppose motion. And the key phrase here is to resist motion, and I should say between two surfaces. I feel like I have to be specific like that, because I can imagine a case where you drop a ball in a river, right? To you, the ball isn't moving when it hits the river, but then the river, thanks to friction, carries the ball away. So you're like, well, wait a second, it didn't oppose motion, it made the ball move. All right, but the friction there was opposing motion between the ball and the river. Forget about you, it's just the ball and the river. So between the two contact surfaces. So that's why I put that little qualifier in there. And the normal force, remember the normal force applies perpendicular to a surface. Friction always applies parallel to the surface. All right, so the strength of friction depends on a few things. All right, it depends on the surfaces that are in contact. So you can imagine that things like, is the surface wet or dry? That's important. Is the surface smooth or rough? And it also depends on the type of material. All right, so these are ways that you can affect friction. So there are actually two types of friction. Two types. The first type that we're going to talk about is something called static friction. And static friction applies in the case when you have two surfaces in contact and those two surfaces are motionless with respect to one another. All right, so you have two surfaces and they're not moving relative to one another. So I'm going to approach this, we're going to take a look at static friction from a simple example. The example of the book on the table that we've used already. Let me see if I can speed up this process by, it's not going to work. I want that one. Is this going to work? All right, so I'm going to have a book on a table, 3 different scenarios, like so. Okay, so in the first scenario, we have a book sitting on a table, and I'm not doing anything to it. I'm not pushing it. All right, like so. So in that case, so I'm not applying a force to it. F, I'll just generalize my force due to me is 0. In that case, the force due to friction is 0. All right, there's nothing to do. The book's just sitting there. Really basic example. All right, but in this second example, I am going to apply a force. I'm going to push the book with a small push. So I'll just use a number as an example. So let's say I push it with 5 newtons. And it looks like I'm pushing it in the negative x direction. In that case, if the book isn't going to move, then the force of friction is 5 newtons in the other direction. Okay, so the book in all 3 of these cases is not going to move. So here I don't push it, it doesn't move because I'm not pushing it, friction isn't doing anything. In this case I push it really, really gently, You can imagine that, I'm pushing this right now very gently. It's not moving. There has to be another force acting on this book to keep it from not moving. That force is friction. So friction is exactly balancing the force that I'm applying. I could keep going and give it a big push. "20 newtons. If the book is not going to move, then it's going to have friction pushing back with the same amount of force. All right, so friction's a little bit tricky in that I can apply a different force, especially static friction. I can apply a different force and I get a different force in response. Does this make sense? Can you imagine, you're pushing something. If I just really gently push the stapler, it doesn't move. If I push harder and harder and harder, it doesn't move, right? That's because static friction, the force that the table is applying to this stapler in the x direction, static friction, continues to get larger as I push on it. At some point, though, I push hard enough where I overcome static friction and this thing moves. All right, and that's something different that we're going to talk about in just a minute. But I can summarize that. So static friction, at some point, I overcome the value. So static friction has a maximum value. So I keep pushing that stapler, and eventually the stapler moves. So I can write that in equation form like so. 0 is the minimum for static friction. But the maximum, there's some value that if I push harder than that, the object's going to start to move. And static friction no longer applies. All right? That value is equal to this. All right, that value is equal to something called mu sub s, which is the coefficient of static friction. All right, mu sub s, this is Greek letter mu. The coefficient of static friction is a property of the two objects and how they interact with one another. So the coefficient of static friction between the stapler and this table is different than the coefficient of static friction between the stapler and ice, for example. So it's a property of the materials. And it's also dependent on the normal force, which you've met already. The normal force. Does that make sense? That's kind of interesting, the normal force. Why would it be dependent on the normal force? So I like the picture of this. So imagine that it's a nice wintry day in Michigan. You get out to your truck in the morning and it's sitting on a nice frozen chunk of asphalt, a good thick pad of ice underneath it. You get in your truck, you turn it on, you start it, and you hit the gas pedal, and what happens? You don't go anywhere. The tires, they just spin, right? So in this picture, the normal force acting on the truck, we'll draw it like that. So what do you do to remedy this problem? You go to your garage, and you get a bunch of stuff, probably sandbags or whatever. I'm just going to load it with a bunch of stuff, like so. In this example then, in this case, the normal force is much larger, right? Because the weight of the truck is much larger. And now the truck will move forward. Because now there's enough friction between the tires and the ice so that the truck will move. All right, so that's sort of why, pictorially, why the force of friction is dependent on the normal force. The harder you push on something, the stronger the friction, that's all. All right, you could have kind of imagined like if you're trying to hold a book against a wall, right? If you just hold really gently, the book's going to fall. If you push really hard, the book stays against the wall. All right, so that's static friction. Let's do a really quick example dealing with static friction. I'm morbid today. I'm going to do the dead body example. So there's a dead body on the floor. which you need to move. Mass is 60 kilograms. The coefficient, because I don't know how to get a mu up here, of static friction is 0.4. I want to know how hard do you have to pull to slide the body across the floor so that you can hide it, of course. You don't like my morbid examples. All right, now notice here when I wrote down the coefficient of static friction, 0.4. So I didn't talk about like sort of reasonable values for static friction, but a value of like 1 is very low, 0.4 to 0.8 is sort of moderate, and then once you get up to 0.9 or higher, those are sort of large values. Notice that there are no units on this thing. The coefficient of static friction is a unitless quantity. There's no units. Okay. All right. So once we do that, though, what we have here is a normal old force problem. So you have a body which looks like a rectangle, and you're pulling the body across the floor. So you're applying some external force. There's a force that's opposing that motion. That's the force due to friction. There's some gravity involved, and there's a normal force. The vectors are not to scale. Let's go to black. There's a lot of green here. So in order to solve this problem, what I want to know is how hard do I have to pull to slide the body across the floor? Now, here's where we start to get into questions that are a bit tricky. This isn't really like there's no specific physics concept in this question per se. What am I asking? So how hard do I have to pull to overcome static friction? So how hard do I have to pull so that I overcome this value? Right? So that's what I'm after. So that says, let me start off looking in the x direction and do the summation of the forces in the x. If I add the forces up, I say, okay, I'm pulling. Opposing my pull is the force due to static friction. What's on the right-hand side? What's the acceleration? All right, so this is where this sort of problem is tricky. Because I'm asking how hard do I have to pull so I just barely overcome static friction, what I'm really asking is this is still 0, but if I pull any harder than that, it's going to start to accelerate. So this is what's hidden in this question is that the force due to friction, I know that it's this maximum value, mu sub s times the normal force. All right? And my acceleration is 0. Because if I pull any harder at all, any little tiny bit harder, I'm going to move that thing. So this is what the question is asking. So this becomes a very straightforward problem then. Force that I have to pull is equal to the force due to friction, which is mu sub s times the normal force. All right? I gave you mu sub s. I didn't give you the normal force. So I got to go dig that out. So in order to dig that out, I got to solve an equation in the y direction. If I add up all the forces in the y direction, I have the normal force pointing up. I have gravity pointing down. And it's in the y direction. It's not accelerating at all. So there's a big fat 0 on the right side. All right. Notice, as I'm going through these examples, I'm shortening them up more as I go along. I'm skipping more and more steps. So if I skip something and you're like, oh, what just happened? Like here, I skipped ma is equal to 0. Stop me and let me know. But I'm sort of assuming you're learning a little bit so I can speed things up a little bit. So in this example, what I'm left with, I do the algebra, is the normal force is equal to the force due to gravity, is just m times g. I'm going to point arrows at this and put stars around it, like so, just so that you realize that this is not always the case. Very, very common mistake when doing these sorts of problems is to just assume that the normal force is equal to gravity. All right? Somebody give me an example when the normal force acting on somebody is not equal to gravity. What? Not when they're moving. When they're... Okay, that's moving. Be more specific.
Not accelerating.
When they're accelerating, okay? If they're accelerating in the upwards direction, the normal force is not equal to gravity. That's the most obvious example. Why do I have a problem with the not moving case? We're gonna quick tangent here. All right, here's an elevator. It's moving upwards at a constant velocity. Oot. There's a 9. There's a person in the elevator. I want to know what is the normal force on the person, acting on the person. All right, so I'm going to write down Newton's second law, which is F, the summation of the forces in the y direction is equal to the force of gravity due to the person minus the normal force of the person. Or I guess I could do that the other way around, how we would normally write our axis. That's equal to mass times acceleration in the y direction. But if they're moving at a constant velocity, they're not accelerating. So this is still 0, and so gravity and the normal force balance out. Okay? So you have to be accelerating in order to have that apparent weight thing. That's key. Constant velocity, they're not accelerating, so the right-hand side goes to 0. Right? This is about to go away. And it went away. Okay, so back to our problem at hand here. So I just solved for the normal force that's equal to the force due to gravity, just in this example. I can go plug this in now to my other equation. So I get the force is equal to mu static times m times g. Now I just plug and chug, so 0.4 is the static friction, mass 60 kgs, and then times 9.8 meters per second squared. My units look good. I get something like 600 times 0.4. Did I evaluate this? 235 newtons. So that's how hard I have to pull. All right, so let me just say, though, we did have to solve an equation in the x direction and the y direction, but it wasn't one of those tricky simultaneously solving two equations, right? Because the y equation, I didn't need to know anything about the x equation to solve that. So yeah, I could have just written this down first, and I would have gotten my solution for the normal force. All right, so most of the time when we deal with problems, I'm probably not going to throw you too many curveballs where you do have to do two equations with two unknowns. All right, we'll do that later on a couple times, but most of the time, you know, if you're getting that, you might have done something harder than you needed to. Yeah, Shane.
Wouldn't the actual answer be greater than 235?
Okay, so yeah, if you pull with 235, this is, you know, a semantics thing. Like, what do you consider to be greater than? Well, 235.0000000 repeating, technically, at some point has to become greater than 230. Yeah, so you're right. Technically, you're right. It has to be just slightly greater than that. But this is sort of like the minimum maximum or something like that. So anything larger than 235 newtons. Any other questions? Nope. Okay, let's introduce kinetic friction. So that was static friction, no motion between the two objects. Once you break that barrier, you get into kinetic friction. So we'll do that next. All right, so just like kinetic friction, or just like, static friction, kinetic friction opposes motion. But this time we have between two surfaces that are moving. Relative to each other. Okay? We have a very similar formula for the force due to kinetic friction. It's equal to mu sub k times the normal force. Looks almost identical, except this time we have this mu sub k, which is the coefficient of kinetic friction. All right? So same sort of equation, different coefficient. In general, mu sub k is a little bit less than mu sub s. What that means, what that implies is that once you get something moving, it's easier to keep it moving than it was to get it moving in the first place. All right, because it's a little bit easier to overcome the power of kinetic friction than it is the power of static friction. I can write that down in a graphic form. So let's do that like this. And I'll draw the x-axis as something like the applied force. And then on the y-axis, we'll do force due to friction. All right, so imagine that you have an object that's initially at rest. Right? And you start to push on that object with some force. As you push, the force due to friction is going to increase as you push so that the object doesn't move. All right? It's going to continue to increase. The object is not moving. This is sort of the realm of static friction. That will happen until you reach some point, which is the maximum value of static friction. So this value right here is mu sub s times the normal force. At that point, the object starts to, if you push any harder, the object will start to move. And so what happens is this happens. And then you get a curve that looks like this. What this says is right at this point, the object starts to move because I've overcome static friction. And then now the only thing resisting my motion is kinetic friction, which just has a constant value. Kinetic friction isn't like static friction where it sort of changes. Kinetic friction has a constant value, generally. Okay, and you notice that this value for the force of friction is less because of this. Usually kinetic friction is a little bit weaker than static friction.